Hello Year 11. So, welcome to a video partly based from the physics labs. And I've come in today to show you this wonderful piece of apparatus and to explain to you how we can use it to investigate the behaviour of certain objects under certain conditions. Now, you might be aware of the problem we have when we investigate objects moving. We have a problem that they stop, and they stop because of the force of friction. So whenever we move something across a surface, friction always acts to basically stop it doing that, and that causes a problem. So that caused, so the Greeks never really had a good view of motion because they didn't really get the idea of friction, and also things like air resistance and so on. It didn't make a lot of sense to them. So what we want to do is to have a device like this, which enables us to remove friction. And this long tube, I'm going to give you a bit of a sense at the end, is basically a bit like an air hockey table. So we have a sort of a pump, an air pump, that pumps through, and on top of the tube are tiny little holes. And so air comes up through the holes, much like an air hockey table, removing friction. If you ever played air hockey, you know that that means that things will move for a lot further. So I'm going to start off with one of my little trolleys. I'm going to place it here, and I'm going to turn the pump on. Now, what you'll notice is it started to drift in one direction, because as long as it takes me, it's really hard to get this to balance perfectly. But if I give it a push in one direction, what it will do is it's going to bounce, and it's going to go back again. And there it goes. And this is because at each end is a little elastic band, so it bounces into the elastic band, just moves back and forward. This is an example of Newton's first law, that an object in motion will just carry on doing what it was doing originally, unless acted on by an overall force. It moves back and forward because we've largely removed air resistance. We've removed friction. Air resistance is still an issue, so it will slow down eventually, as is the slight tilt on this, which means it again won't be perfect. But it will just keep moving. Yeah, it's slowing down a little bit now, but it's as good as we can kind of get it. Now, as fun as that is, the reason that I brought this out is because I want to investigate what happens when one object collides with another object, a collision. And the idea of, can I predict what the speed of something will be after there's a collision, after there's an impact. So the setup of this is I'm going to have one trolley, which is going to be placed there. It's going to travel through. It's going to collide with the second trolley and move through, and then we've got a second light gate here. So I can measure the speed before and the speed after the collision, and look for something that may be constant before and after. In science, it's about finding something that you can say is going to remain the same, because that is what allows you to make predictions after an event. Okay, so conservation laws. Stuff like the conservation of energy, or the conservation of mass, the conservation of charge. Is there something that we can find which will be conserved before and after this collision, which will allow us to work things out? But let's start with a very simple question. I'm going to have a spiky bit on this one, and I'm going to have a sort of bit that it's going to collide with. Set them up. I'm going to push this one through, and after they stick together, what do you expect, given they're the same mass, to happen to the speed? So what do you think is going to happen? What will the number be from there to there? And let's see. So what you're looking at here is the data logger, which my light gates are connected to, just so you can see the results as they come in the incredible excitement. So I'm going to turn it on, push it through, and we'll see what numbers we get. The top number will be the speed of the single trolley. The second number that comes up is the one when they have joined together. look at that. 0.55 meters per second to start with. They join together, speed drops to 0.26 meters per second. It drops by about half, which should make sense in some ways, because this object on its own, when it's joined together, suddenly that's double the mass. The mass has increased. The speed has halved, or the velocity has halved. So that makes sense. Let's investigate some situations where we have slightly different masses. Okay, so what we're now going to do is take a result where we change the mass of these things as they collide. So the first thing I'm going to do is I'm going to add some mass to one of these. Now this on its own is 200 grams. Now adding these metal discs to it, these metal discs are 50 grams each, so the mass of this is now 300 grams. Same experiment, same idea, going to push it through, going to collide with this one, and we're going to see what happens to the velocity after the collision if we've got a heavier object sticking to a lighter one. And then what I'm going to do is I'm going to reverse it. So the heavier object will be stationary, the heavier object will be here, because I'm going to put the discs onto this one, and then I'll push it through again. And then we'll see what happens to the speeds in that sort of change of scenario. So. So the next result you're going to see is the heavier one doing the collision. So the heavier one is moving at the start. Now you're going to see a result where this one is the one we'll collide with. So here are the results that we've taken, and I'm introducing a new physical quantity. It's called momentum, and it's the product of the mass of an object multiplied by its velocity. It is a vector, so it has a momentum in a particular direction. So you have something going left or right. And it's got a unit of kilogram meters per second, because it's the product of mass, which is in kilograms, meters per second, which is velocity. So you get a unit of kilogram meters per second. And momentum is quite an important thing, because what we have is these are our results. We have the mass before the collision, which is of the single trolley, and the velocity before the collision that trolley was travelling at. And then after, we've got the mass of the two trolleys stuck together and the velocity of them when they were stuck together. And what we can do is we can look at the momentum before the collision and after the collision and see if there is something to be observed about them, which there is, because otherwise, why would I be doing this? So we can work this all out. If you want to, you can pause the video, you can sort of work these out yourselves and see if you notice something, but let's try going through that. So the other thing that's important is all of my data is collected to two significant figures, okay? So two significant figures. That is as accurate as I can write anything in these tables. I can't, although you might find that your calculator spits out large numbers, you know, that go on for a long period of time, I can't use those because I'm only confident about these to two significant figures. So all my answers are going to be the same significance. So if I put 0.2 times 0.55, I end up with a thing of 0.11. Similarly, 0.40 times 0.26 gives me 0.104, which I therefore have to say is 0.1. When I have the heavier object, so 0.3 times 0.5 gives me 0.15. 0.5 times 0.29, also to two significant figures, gives me 0.15. Here, 0.2 times 0.61, I get 0.12. And 0.5 times 0.23, wonderfully, I also get 0.1. And that is the power of calculating the momentum of something. Whenever two objects collide or interact in any way, as long as we can remove constraints like air resistance and things like that, what we find is that the momentum before the interaction is the same as the momentum afterwards. And what this means is that we can always sit there. If we know the momentum of something beforehand, so we know its mass and its velocity, and we know it's going to interact in some way with another object, we can work out the speed of velocity of that object after the collision. Okay, so it allows us to say, well, this number should be the same before and after your interaction. And that's the power of calculating the momentum. It's called the conservation of momentum. It's one of the things in physics that is conserved. So before and after collisions, these things occur. And this is why when you have certain things, you get this ability to predict, because it isn't just in the case of two things, of one thing bumping into another and then drifting off entirely. The conservation of momentum will also apply when if you have two objects that collide and they both carry on moving, or if you have two objects that are traveling in opposite directions and interact, or if you've got something like a cannon and you fire something out of it and one thing goes one way, one will have to go another way in order to conserve momentum, because it's one of the things that before and after any interaction, these things must be the same number. And there we go. It worked. So momentum is something that is conserved before and after a collision. So we're going to make this problem slightly more complicated. What happens if these two things are moving? So we don't just have one stationary and one moving. What if they're both moving? And in fact, what if they're moving against each other? So it's a head-on collision. So what I'm going to do is I'm going to push them apart. They're going to each hit the elastic bands that are at either side, and they're going to bounce back in, and they're going to meet hopefully around here. They're going to be moving in opposite directions. And so, make a prediction. What do you expect to happen if I'm able to do it so that they have approximately the same momentum, but in opposite directions? So let's see. There we go. By moving in opposite directions, they've got opposite momentum, one positive and one negative, and when you add it together, you're going to end up with about 0, and so they stop. Near enough. Voila!